Hello guys. So in this video we are going to discuss about Chinese remainder theorem. Chinese remainder theorem. Okay. In short, we write it as CRT and it is very common. So we will call it CRT from now on. Well, what is Chinese remainder theorem? So Chinese remainder theorem says that if there are equation and let us say there are equation, let's say x0 is concurrent to a1 mod m1, x is also congruent to a2 mod m2, and similarly there are r such equations. So x is congruent to ar mod mr. Okay, there are such equation such that GCD of mi mj is 1 for all I and j, where I and j are less than equals to r, and basically for all from 1 to r and I is not equals to j. Okay, so all these m1 and m2 are relatively prime. So GCD equals to 1 simply means it's relatively prime. So m1 and m2 is relatively prime, m2 and m3, m1 and m4, and so on. So all the pairs are relatively prime to each other. So Chinese remainder theorem suggests us a way, or give us a way via which we can solve these equations, and basically we can find out the value of x. So given this equation, the intention is to find the value of x, or the first value of x. So basically this equation, since it's a modular operation, so there would be multiple solutions to it, but what is the first value which is going to satisfy this problem? So that is something we can use Chinese remainder theorem to solve this problem. Okay, now let us see what the Chinese remainder theorem says. The solution for this problem is basically x, and that x can be given by the equation this I equals to 1 to r summation m over mi into ai into bi. Okay, so let me define this term. Okay, and this is, by the way, this is the solution which Chinese remainder theorem gives us, that if you have such an equation, then the solution, the first value of x can be obtained by solving this particular equation, by expanding this equation. Now let us look at various component of this equation. So the first question which would arise is what is this m, right? What is this m? Okay, so m is basically equals to m1 into m2 into m3 into mr, right, all the way till mr. So the product of all the m's which we have in this equation, so like this, the product of all m's is given by m. Okay, now what is mi? Now the other question would be, what is this? Ai is clear because ai is part of our equation. What is this bi? Okay, what is this bi? So bi is basically is multiplicative inverse of multiplicative inverse of m over mi. Okay, so bi is the multiplicative inverse of m over mi, and we will see how can we compute the multiplicative inverse of m over mi. Well, the way we will be able to compute multiplicative inverse is extended Euclidean algorithm. So here, to find it, we can use extended Euclidean algorithm. Okay, now let's go on go on with the proof. So this is what we want to prove it. So before we prove it, there are general so let us write down all the things which is given to us before we begin with the proof. So the things which are given to us are basically m is equals to m1 into m2 into m3 dot 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 mr. Okay, and we know that GCD of mi comma mj is, so GCD of mi comma mj is equals to 1. This is also something which is given to us. Okay, now let us compute the GCD of m comma mi divided by m comma mi comma mi. Okay, so let us say I equals to 1. So essentially we want to compute the GCD of m upon m1 comma m1. Okay, so this is basically GCD of m comma m1 divided by comma m1. Okay, now since m equals to m1 into m2 into dot 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 mr, and we are dividing this equation by m1, so m by m1 becomes m2 m3 till mr, right? So basically m upon m1 does not contain m upon m1 does not contain m1. So GCD of m comma m1 comma m1, since there is no common factors here between this term, let me just use a different thing, between this term and m1 there are no common factors, right? And since there are no common factors, then the GCD is 1. Okay, so similarly we can plug I equals to 2 and we will see that the GCD of m comma m2, so similarly we can say that GCD of m comma m2 comma m2 is also 1. So in general we can write down GCD of m comma mi comma mi is 1 for all I, where I is less than equals to r and I ranges from 1 to r basically. Okay, so that's about this. Now if you using this, basically we would be using this, we will be able to find out the, now since m upon my and we wanted to find the multiplicative inverse, so if you express this equation in the form of ax plus by and use extended Euclidean algorithm, we will be able to find out bi's here basically. Okay, so that's a little detour there, but I thought it would be so basically let me write it down. So let me say GCD of, we know that GCD of m comma mi equals to 1. So we know that m comma mi into x plus mi into y equals to 1, and x is the multiplicative inverse, right? Multiplicative inverse. Okay, and here we can say that x equals to bi. Okay, I mean x will differ once we put the value of I equals to 1 and 2 and 3, so similarly x will become b1 b2 and so on. Okay, so that's about till this portion. Now let us expand this and see what do we get once we expand that. Okay, so basically the solution is given by x equals to, according to Chinese Remainder Theorem, the solution will be given by x equals to I equals to 1 to r and m over mi into ai into bi, right? So let us expand this. So this essentially means x equals to m upon m1 a1 b1 plus m upon m2 a2 b2 plus m upon m3 a3 b3. Just a second. Dot 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 m upon mr ar br. Okay, so this is the equation which is given to us. Now let us do this. Let's call this as equation 1. Perform, or let me use a different ink. Let me use a different ink for this. So perform modulo m1 operation on LHS and RHS. Okay, so we will perform modulo m1 operation on LHS and RHS. So now this basically becomes x modulo m1 equals to m upon m1 a1 b1 modulo m1 plus 0, right? All these terms, basically, if you look at all these terms, if you divide these terms by m1, then the remainder will be 0. The reason is because all these m's which are there, that m over m2, m over m3, m over mr, all these terms will contain m1, and hence this entire term will become a multiple of m1, because of which all these entire terms when divided by m1 will translate to 0. Okay, so because of that we can write this equation as x is x modulo m1 equals to m by m1 a1 b1 mod m1, right? So this is what we can write it down. Now let us look at this. X mod m1 is equals to m upon m1 b1 mod m1, and this entire term multiplied by a1 mod m1, and then this entire term is mod m1, right? Distributive property, basically distributive property. So I have just, I mean, this is equals to this if you we can distribute it like this. Okay, I mean, if you read more about the distributive property of modulo operation, you will see that these two terms are same. Okay, now now let us look at the value. What will be the value of this term? Okay, now the value of this term is 1, basically. That is what I wanted to come up with. So let's see why it is 1. So we know that GCD of m comma m1 is 1, right? We know that, we know it from here, right? We were doing all these things and we know that GCD of m comma mi equals to 1. Now since this is 1, so this can be expressed in this equation. So let me express it in that form. So this is basically equals to m upon m1 into sorry about that, into b1 plus m1 sum x equals to 1. Now let us take a modulo m1 operation on both the sides for this equation. So taking modulo operation, so this becomes m upon m1 b1 mod m1 plus m1x mod m1, right? And this is equals to 1 mod m1, right? So this term, you can see this term evaluates to 0. So this we can write it down as m upon m1 b1 mod m1 equals to 1 mod m1, right? And this we can write it down as m upon m1 b1 is concurrent to 1 mod m1, right? So now put this here in this equation, right? So this will be substituted by 1 mod m1, right? So rewriting this equation again, we can write it down as x mod m1 equals to a1 mod m1, right? Let's go further and look at why we are at. So this basically, this, if you see, this translates to 1, right? This translates to 1, and this I am writing it as it is, right? So that is how this becomes this, and we can let me use a different way. So x is, we can rewrite it as x is concurrent to a1 mod m1, right? Similarly, if we, so right now we have divided this equation, remember this equation, we expanded this equation and then we perform modulo m1 operation. Similarly, if you perform m2 operation, all the terms except a2 b2 m over m2 will be will evaluate to 0, and we will perform similar kind of substitution which we have done here, and we will come to a conclusion that x is concurrent to a2 mod m2, right? Similarly, for r, this becomes mod mr. Hence x is the solution, which will be given by x equals to summation I equals to 1 to r ai bi m over mi, right? So this is how we prove the CRT theorem, Chinese Remainder Theorem. That's about this video, folks. If you have any questions or comment regarding this proof, or if you have any confusion regarding this proof, please feel free to drop a comment and I will try to address them. Thank you.